This is lecture 18 of Surveying 1, and in this lecture we are discussing the topic of traverses and traversing, and it's kind of the terminal point in terms of the material we go through in the course, although it isn't necessarily the end of the course. We'll be building out some of the areas that we have already covered for the rest of the term. So a traverse, what is a traverse? Let me just review that again. It's a series of connected lines where the angles between them are measured and the lengths of the lines are measured. And traverses can be open or closed, and we'll talk about that here shortly. And by open or closed, I mean geometrically. But there can be another meaning to the words open and closed. So I say if they are open, they can still be closed in the sense that angles and distances measured can be checked against some kind of benchmark. So let me talk about geometrically open, and maybe I should start by talking about geometrically closed. So here's a series of lines where we measure, let's say, all the interior angles and we measure the lengths of the sides. Well, this traverse is geometrically closed, which also means it's mathematically closed. What do I mean by that? Well, there are several things you can check. The first is that the angles all add up to the theoretical value of n minus 2 times 180. You can also do some calculations, which we will not cover in this course, but which we will cover in the next course, that will allow us, if we begin at a certain point, to actually calculate where we've come if we use the bearings, the distances and angles we measured to see if we end back at the point we started from. So this is kind of a fundamental part of surveying, where possible to end where you began as a way of creating a check. So when it's geometrically closed, you have lots of those things available to you. If it's geometrically open, it means it's a traverse that looks like this, perhaps, where it starts and ends kind of hanging. It doesn't close back on its point at the beginning. But it may turn out that this first line, this first angle that's measured, that there is a known bearing or azimuth for that line. And it could be that there's a known coordinate. And so when we talk about coordinates in surveying, we refer to them sometimes as the northing and the easting. Again, we will get into this more in surveying too. And then you can use these angles that you measure and the distances you measure till you get to the end. But it could be that the end is actually here, and that this last line is simply a way of checking your final angle. So this final angle, if you calculated all your directions through here, your final angle should come up to some check value that you already know for this last line. And if you also have coordinates, meaning a northing and an easting for this point over here, then you have essentially a mathematically closed figure, even though it's geometrically open. It's as mathematically closed as this figure here on the left. And that's the difference I want you to understand. That's entirely possible. In fact, when most cross-country surveying is done for various projects, whether they are highway projects or geodetic surveys, it's very common that they're geometrically open and yet mathematically closed. So I just wanted to emphasize that when they are geometrically open and mathematically closed, first of all, you have starting and ending positions known. And I'm going to write here starting and ending coordinates as my shorthand way of saying that. And you also have starting and ending directions. So you start with a direction and you end with a direction. And if you remember, when we go back to the geometrically closed traverse, if this happens to be the first point we started at, so let me just call these A, B, C, D, and E, When we start at the first point and we measure the distance b, to measure this angle, we actually have to look backwards to what we would call the previous point, even though there's, in theory, there's no previous point because A is the starting point. And this is a really important thing to remember, that in a geometrically closed traverse, that you measure all the angles, which means you have to occupy point A and measure to point B, then you occupy point B and measure to C, and so forth. But when you occupy point E and you go to point A, if you didn't measure this angle when you started, then you may need to reoccupy point A to measure it, because it could be that when you start your project, and now I'm talking about traverses that could have dozens or hundreds of legs, that you may not know where the equivalent to that point E is. So when you start, you don't have that starting angle, so you eventually will need to go back and reoccupy your starting point to make it a geometrically closed figure. So that's something you should be also aware of. That is often a failure that occurs with people who don't know or have much experience with surveying, and it's similar to forgetting a backside in leveling and so forth. All right, so in terms of the computations in this section of the course, the computations that we will be covering when it comes to traversing is to checking angles and computing the directions in a traverse. We'll also talk about adjusting the angles if they don't add up to n-2 times 180. But we will leave most other computations to surveying 2. So balancing angles, how do we determine the level of angular closure? And it depends on the traverse configuration. So what do I mean by balancing angles? Well, let's just talk about a geometrically closed traverse. So we want these angles to, or we check these angles to see if they add up to n-2 times 180, because if they don't, then that's kind of an indication that we have some kind of a problem. So the first question is, how do we determine level of angle of closure? So in this particular case, we have 1, 2, 3, 4, 5, 6, 7. So 7 minus 2 is 5. 5 times 180 is 900. 900 degrees. So let's say we miss it by a degree. Well, with the kinds of instrumentation we use in this class, that would be indicative of a blunder, or maybe more than one blunder. What if it's off by 30 minutes? That would still be so, and so forth. So how do we know this? Well, it's a judgment thing. It depends to some degree on traverse configuration. It depends on what the purpose of the survey is. It depends on the instrumentation that's used and the quality of the people and the quality of the instrumentation that's used. But if you have an instrument that can read to 1 second, and let's say its nominal accuracy is in the 5-second range, then you would want something like, for an acceptable error of closure, of angular closure, 5 seconds times the square root of 7 to be kind of your maximum value. So it's not a whole lot. And so you can see here that if we had 9 sides in this traverse, 15 seconds would be the allowable limit. Now, in the exercises you'll be doing, we generally will allow you more than this because you are not experienced surveyors. But this is just to give you an idea that the typical thing is to say, well, how much reasonable uncertainty can we expect with the procedures, the equipment, the conditions, and so forth that we've got going? Or it may be you actually have very high quality procedures and equipment and so forth, but the purpose of the survey is such that maybe you can tolerate 30 seconds per angle. So you come up with that value, whatever that value is, and it's most typical to then multiply by the square root of the number of angles that you have in the traverse. So that's what I'm getting to, how do you determine the level of angular closure? Now, what we do is we balance them. So let's say in this particular traverse that the angles were in error, or that they didn't add up to n minus 2 times 180. They missed by 10 seconds. We were 10 seconds short. So this would mean that we would need to correct each of these angles equally, but it doesn't make sense to divide by 7, figure out some decimal number, and say we're going to correct each one by 1 point, blah, 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 blah. So what we typically do is we look at the traverse, and we might have reasons why we might say, you know, instead of giving a 1 second correction to this one, we're going to give it a 2 second correction. And we'll put a 1 second correction here and here, so that's 4, 5, 6, 7, 8. So we still have 2 more seconds to distribute somewhere. And so you may look at this and say, well, we had difficulty citing this because we're going across the road and so forth. So maybe there's some error there. And for the same reason, because we're citing back, it's there. So 2 and 2 is 4, 5, 7, 8, 9, 10. It now adds up to 10. So you kind of do that arbitrarily, but you adjust the angles so they add up to perfection. That's always kind of a step. Every step needs to be looked at. Can we somehow figure out how to adjust it? And this is related to the next topic that we will come to after this next series of, after this lecture, which is to go back to the early part of the term and go back to the concept of errors and blunders and mistakes and accuracy and precision, and go through kind of the material that we've gone through so far in surveying and start to apply those principles that we kind of ignored for the most part when we first encountered them. So that's how you balance angles. You balance angles so that you do get the geometrical value that you're supposed to get. Geometry demands that a 7-sided figure should have its interior angles add up to exactly 900 degrees, not a second more, not a second less. And so what we do is, after we make our measurements, understanding that we're not capable of making perfect measurements, we will always have some angular error or angular misclosure, as it's sometimes referred to. And then we need to figure out how do we redistribute the error. Now you notice I said minus 10, so you would add these numbers to your measured values to get your balanced angles. If, on the other hand, you came up with a plus 10, then you have 10 seconds too much, and so you would subtract these values off the angles you measured to come up with your balanced angles. So evaluating angular closure, the basic thing is that it's x times the square root of n, where n is the number of angles in your traverse. Not the number of sides necessarily, because that can be confusing, because if it's a geometrically open traverse, your last 2 lines don't count, so you actually have to look at the number of lines, the number of angles you actually measured. And x varies a lot. Very often it's the least count of the instrument. LC stands for least count, and this is the lowest value you can read on the instrument. And this generally applied to non-electronic instruments. So we used to have, for example, transits in the old days that read to 1 minute. So you would use 1 minute for the least count. Some transits read to 30 seconds, so you'd use 30 seconds. Some read to 20 seconds, and others read to 10, and so forth. Once the electronic instruments came out, they became a little bit different in how you evaluate. So there's a value called the DIN, or sometimes it's called the ISO accuracy value. And if you look at the spec sheets, you will see this. And most instruments out there in practice today, you actually have to look at the spec sheet for the instrument to figure it out, but they're somewhere in the 1 second to 10 second range. And so once you get really good with your instrumentation, I'll start having you use 10 seconds for X. but it's not uncommon for students to then take that 10 seconds and then multiply it by 2 or 3 just to cut them a little bit more slack, although most professional surveyors would never find that kind of thing very acceptable. So I want to talk a little bit about finding mistakes in traverse angles. So when you have a figure that's closed and your traverse has an angular error, so the angles don't add up, but it's off by a lot. Maybe it's a degree or half a degree or 2 degrees or 10 degrees. One of the things you can do is that you can compute mathematically what the error is in your traverse. So you might wind up with a gap like this. In other words, you physically measured all the angles, you physically measured all the distances so that it closed. But it turns out there's a gap because of some problem with your traverse angles. Now, if you haven't done this mathematically, or if you don't know the techniques for doing this mathematically, you can also plot. You can plot every line to scale. You can plot every angle to scale and see how much the beginning and end, which is supposed to be the same, miss by. And then what you do is you draw what's called the perpendicular bisector, and the perpendicular bisector will point to the angle that's most likely the cause. Well, in this case, it falls kind of between these two. It's closer to this one. So if I was doing some investigation, and I've actually experienced this in the field, where I had maybe a 50-sided traverse, so that's a lot of work to go back and remeasure everything, so you resort to this technique. And I've actually had situations like this where maybe I had a 1 degree error or something like that, pointed in between, so I go out and check this one, and a particular case I'm remembering, I actually found half the mistake, half of the 1 degree, so about 30 minutes. So since I didn't have the facilities to replot everything with that angle, I went ahead and checked this one, and as it turned out, this had a problem. That's not always the case, however. My point is, if you find some of your mistake and it drops from 1 degree to, let's say, 10 minutes, 10 minutes is still a fairly large error, and if you have a large traverse, you will definitely have a gap and you will have a perpendicular bisector you can draw, and it may point to a completely different angle than the very next one, as it happened in my particular case, the most tedious one that I ever had to do in real life. So something to remember, that the perpendicular bisector will always point towards a likely suspect. Your problem may be that you have more than one culprit, and so it'll point maybe in the direction of the biggest problem, or sometimes to some direction that's between your 2 big problems. And so it gets to be kind of a hard thing to do some detective work there if you have more than one angle that's problematic. I want to talk a little bit about field notes. So there's different ways of taking field notes, and this is only one way, but you really need to think about how you measure a traverse, because especially for students, getting it organized, understanding what you're doing your homework, doing your preparation, reading the textbook, listening to the videos is not always done perfectly. So I just wanted to give you an example of a way that you could possibly take field notes. So in this particular case, here's what I have. I have 2 angles that were measured. We don't know what the traverse looks like because all this is the left-hand side of the pair of fieldbook pages. So the right-hand side is off the screen here. So I have my 6 columns and I've labeled them as you see here. So where it says angle, I've written angle HQ17. Now there's a very specific meaning to that. It means that I am set up at Q, I'm back-sighting H, and foresighting 17. Very important, because it's common practice very often for surveyors to say, oh, I'm measuring angle Q, or I'm measuring angle B, and so forth. The problem is you don't know what's been back-sighted and what's been foresighted, so sometimes when you have two lines intersecting, there's a big question which angle was actually measured. And here's what I'm talking about. If you have two lines like this, you could measure this angle or you could measure this angle. And if this is H and if this is Q and this is 17, then it means I back-sighted H and then I foresighted 17 while set up on Q. So that would definitely mean this angle out here and not the one below. 17QH on the other hand would be the other one. So you need to get used to that style of notation and that style of terminology expected of you. Now, I've said that I wanted angles measured direct and reverse, or to put it in more modern terms, in phase 1 and phase 2. You really need to get familiar with your instrument and figure out what that means. When you are sighting with your instrument in phase 1, your angles will be in the range of 90 degrees. When you're sighting in phase 2, your vertical angles will be in the range of 270 degrees. And I don't mean exactly 270 degrees. It might be 265, it might be 275, it might be even far more or far less than those, but they won't be anywhere near 90, because 90 will only be possible for your vertical angle if you're observing in phase 1. And why do I talk about the vertical angle? It's because on our modern instrumentation, it's hard to know when your telescope is upside down, unlike with the older transits. So you have to look at that vertical angle to give you some guidance. So put the instrument in phase 1 and you back sight angle, point H. Now what I have said is you can hit your 0 set button because you have an electronic instrument to have you read 0. Many of you have not developed the very, very soft touch that's required to measure angles accurately. This is one of the reasons why I allow you far more as a tolerance for angle measurement than a professional surveyor, an experienced surveyor would get. So once you've pressed 0, two things are working here against you to get perfectly 0. The mere fact of pressing on the button will cause the instrument to move off the point. So the first thing you do is you look through the telescope and get a hold of the tangent screw and move the crosshair back to the point, because more than likely it has moved off. Now you could hit 0 set again, but you're going to be just doing the same thing over and over and over again, never getting to 0. So what I tell people is move the crosshair back to the point and then read off the value. The value is not your angle, it's your backsight reading on the horizontal circle, as it's called. And in this case, I've used 8 seconds as my example. And then to read your angle, you now turn to your foresight and record 49, 12, 18. And one of the things your note keeper should be doing, that's regardless of whether you are the instrument man or your note keeper is an additional person on the team, you should be checking your angles as you go along, which means you need to be doing your math. Well, here you can see that we started near 0, we got to 49, 12, 18, but we are past 0 by 8 seconds, so it should be very easy for you to get to 49, 12, 10 without doing a whole lot of thinking. I'll come back to the distances in a second. Now you invert your telescope, and to give you the experience of measuring in a different way, what I want you to do now, your instrument is now in phase 2, now you go back to your backsight reading, which is point H, and you simply read off whatever it has. And it says 180, 00, 12. Well, there's a check there because you're within 4 seconds. There's a difference of 180 because you've inverted your instrument, but there's only 4 seconds difference, which shouldn't be of great concern because there are many adjustments in the instrument that may prevent it from displaying exactly 180.0008, which is kind of the theoretical number you should have if you got a backsight reading of 0008 in phase 1. Now you turn to your foresight, point 17, and you get 229, 12, 16. And I keep telling you, you need to learn to do this in your head or to reduce this very fast with your calculator. So if you've done everything right, obviously you should get something close to 49, 12, 10. Well, how do you do this? Well, 16 minus 12 is 4, so we can write the 4 down there. And we can tell here that we have 12 minutes, and now you only have to take 180 away from 229. Hopefully you can do that in your head and come up with the 49. And then you average those two to come up with your mean value, which is what I have on the 4th line. So you see I've used 4 lines to measure one angle in the traverse, where we have measured that one angle twice, once in phase 1 and once in phase 2. Now the other thing you should do on your traverse is measure a distance whenever it's possible. So if there is a prism that happens to be there on your foresight point H, you should measure distance to it. That's why I call it distance back, because from Q to H is the backward looking distance. Q to 17 is the forward looking distance. Then you measure forward and you press the distance button and you get 275.38. Then in phase 2 you got 2 other numbers here, so you can average your distances. Then you move up your instrument to point 17, and so now you have Q17J. J is your next point in your traverse. And you repeat the whole process. Here I used a slightly different example. You see here, instead of 0008 or 000 exactly, I have 359, 59, 57, which means that's the equivalent of a negative 3 seconds. Because if your instrument rotates accidentally in the other direction, that's what you're going to have. Then you rotate to your foresight, point J, and you get 67, 12, 38. Now, how do you figure out how this angle works? Well, you know it's 6712 in that region because this is close to 0. But you're behind, if you will, the 0 point by 3 seconds. So to get our net angle, what we do is we add that 3 seconds to the 38 to get the 41. Then we invert the telescope, we come back to our back sight, and this time we get 180.0001, 247.12.38. Again, you need to calculate what this is. So you have 38 minus 1 second is 37 seconds, 12 minutes, and hopefully you can do this in your head. 247 minus 180 is 67. Then you average those two together to get the 67.12.39. And as you're backsighting and foresighting, you should also be measuring your distances. So I've done the similar thing to what I did up here to get a back and forward distance in both faces. And obviously one of the things you should be doing if you're the note taker, you have a big responsibility to make sure that these two distances are coming out approximately the same, because when you're finished with your traverse, you should have measured every distance 4 times if you have a prism on that back point. And so what you do is now take the average of the 275.41 and the 275.39 to actually get the average that you should be using for your calculations in your traverse. Now we don't use those numbers for calculation in our traverse, but I will still, there'll be times when I will ask you to still compute the average distance, the average of the 4 distances. Keep in mind that this is only one of the ways you can collect angles when you're traversing. There are many other ways to do it. You are free to select any possible way you want to do it, but make sure that you are writing carefully, that you do not erase, that you use a hard enough pencil that nothing smudges, and if you do make a mistake, you draw a single line through it. Why? Because sometimes when you make an erasure or a correction, sometimes you made a mistake and you need to go back to the original value. And right next to it somewhere, you write in the correct value. Doing the math is really important, and carrying a calculator in the field for this kind of thing is really something that slows you down tremendously, and you need to develop much better skills at mental arithmetic, because this is really fairly simple. All right, so I want to talk about side shots. So let's say we have a traverse, and this is just sketching part of a traverse that may be geometrically open or closed, it doesn't matter. But there's a reason to locate auxiliary points. In other words, you're running this traverse because it's performing a function of being kind of the controlling backbone to a survey you are doing. And you know that at some point down the track, you will need to come back and locate some beacons that are located here for an airport runway. There's an airport runway that heads off in this direction here somewhere, and these are some of the beacons, and you need to locate them. So one of the things you can do as you're running your main traverse, or sometimes you come back depending on how much of this you need to do, what you may do is, even though you're running your main traverse and measuring these angles and these distances and so forth, is that you can also have additional lines for recording angles to these side shots. So after you have backsighted this point, you would foresight this point for your main angle in phase 1 and phase 2. But you can also sight this point so that you would be actually measuring, let me use a different color, so that you would be actually measuring this angle, and of course you'd be measuring this distance. And you would do that in phase 1 and phase 2 sometimes, and sometimes only in phase 1. A good example of when you would do phase 1 only might be when you're doing things like topographic mapping. But if you're locating something that's needs to be really located accurately, but it happens to be something that's 6 feet in the air, so you can't set up the instrument over it, you need to locate it very carefully, you would do that. In fact, if you had to really locate this thing extremely carefully, one of the things you might do is when you moved up to this next traverse point, you might also observe this line by backsighting this point over here, your previous point in your traverse, and measuring this angle in phase 1 and phase 2. So you're getting a location for that point from 2 different traverse stations. They don't have to be consecutive traverse stations. Sometimes it's possible that you might do something different. For example, to locate this point, maybe because there's trees and so forth in the way, the first time you measure this angle in phase 1 and phase 2, but to locate it from a second traverse station, you do it from here. So these kinds of things can vary. There might be linear features like a stream, a river, where you want to locate the banks or the center line of a ditch, a road, a sidewalk, and so forth, and could also be property corners. So instead of this being an airport, this could all be part of a subdivision, and there's actually lots, and you need to locate the ions that you found as you were doing the research for the property corners, and you might locate them in these similar ways. Sometimes when there's just a few property corners, and if they are all points that you can set your instrument up over, you might occupy them, as the term is used by surveyors. But many times there might be fence posts, trees, pillars, many other kinds of things, and in downtown areas, for example, where you have zero setback, you might have building corners that are literally on the property corners, so you can't set up over the point, and so you need to take side shots like this to locate them. And as the value of that location gets more and more expensive, so downtown building, an airport beacon, and so forth, they need to be located with a much higher degree of accuracy than, say, a topographic mapping shot. You might do things like observe it from 2 different traverse stations. So I want to talk about a few field procedures that you may or may not do in this class, but you should be aware of that is still done. So sometimes we have a situation where we have two lines that intersect. And this might be where we have traces of a fence that we find here, and we want to extend this fence out, and we find traces of a fence here and traces of a fence here. So we can kind of draw these lines, and we want to figure out where this point of intersection is. So one of the most common ways to do this is for surveyors to set up on these 2 points and kind of estimate where they think the lines intersect, and they might set 2 stakes on either side of where they think the lines intersect. They know it approximately. They would do the same thing in the other direction. And once that's done, they would actually extend strings between the nails on top of 2 stakes here and the nails on top of 2 stakes there to find and mark with a stake and maybe a nail the exact location of where the 2 lines intersect. This seems rather quaint for those of you who have practice doing professional surveys, because you know with the computational power you have in your total station or possibly in your data collector that it's possible to actually do a mathematical calculation of this. And when we get to surveying 2, we will talk about that. But there are many times when, especially in the construction environment, where you don't have enough information to do the mathematical calculation, and you have to physically extend those lines and figure out the extension using things like strings and stakes and nails and so forth. So I just wanted to point out that a surveying instrument is really great for defining the lines by setting up on 2 points that are supposed to indicate where these lines are. It may be those 2 points, it may be a point here and a point there, so you extend them out, and then you set these 2 points on line here, and then you do the same thing over here. Then these are close enough together where you can run string between them to find the exact point. Also, I want to talk about the concept of cutoff lines. So when you have a large traverse, and this is not a super large traverse by any means, but I just wanted to put this in. Let's say you have a traverse that runs, as I have run, and many of you who work in surveying have run, traverses that might run a couple of hundred sides. And one of the big problems when you have one of those is that it's inevitable that some kind of a blunder gets committed, and sometimes it's more than one. And trying to figure out where these are and figuring out where to remeasure without completely redoing the entire survey is hard. So one of the things surveyors have learned is to run what are called cutoff lines as part of their survey when they run the main traverse. So they might, in addition to running this traverse, we haven't talked about why traverses are located the way they are. We'll talk about that in surveying 2. But you might run this, so you might, in addition to measuring all the sides and angles in the lines are marked in red, which is a principal traverse, you might also measure that angle and that distance. And when you get here, you might measure that angle as well. And maybe you do that in another place like this, for example, where you measure that distance and you measure that angle and that angle, for example. And what that does is it allows you to calculate around those traverses that are sub-parts of the main traverse, because you have these cutoff lines, and you can see if the sub-parts are able to stand alone on their 2 feet. And if they are, then you know that if you calculated this one, and you know that this one is okay, and this one checks out, then you know that the problem is in here. Now, if this thing is 200 sides, it may still be too large, and so one of the things you might do then is start to look for what we call intervisibility, like, oh, I can sight from here to here, so you set up here and you measure these angles so that you can now, by process of elimination, zero in on a fairly limited number of sides and angles that you need to check to perform new field work so that you can properly calculate the survey. want to talk about angles that need to be measured that can't be occupied. And a very common one is where you have a fence like this and a fence like this, but you can't set up your surveying instrument where those two lines intersect. So you don't really know what this angle is or what this angle is. And so the most common way to do this was the following procedure. And again, this may seem quaint to some of you who are aware that you can do this a number of different ways with fairly sophisticated computing power and software in your instrument or your total station. But I just want to point out that there is a kind of an analog way to do this, which sometimes you have to fall back on, especially in construction situations or some unique situation that does not allow you to make measurements the traditional way. And so the most common way to measure these angles would be to find the straightest fence. And what you would do is you would take 2 points on this fence and you would essentially measure at right angles to the fence the same distance, such that we have now created a line that's parallel to that direction. And then we would do the same thing over here. And we have that line. So now, using the previous procedure we talked about, you could intersect these two lines, you could set up here, and because these two lines are parallel to the ones you're interested in, you can now measure that angle to figure out what that angle is, and once you know that angle, you can figure out all the other angles, assuming that these lines are straight. Again, this is not a common problem for most surveyors today because they have all these mathematical tools, these programs at their fingertips in the field with electronic instrumentation and data collectors. But be aware that there will be times when you will run into this situation where either your batteries have just died or something else has happened, where you may have to resort to analog procedures to come up with some of these answers. So that's the reason for discussing this, because this, doing things this way, demonstrates your understanding of what the heck is going on, rather than doing something by rote and simply pushing buttons and not being able to talk about what you accomplished. I want to talk about prolonging a straight line. So let's say we have 2 points over here, and we want to know where that line is when it gets to, let's say, the bank of a creek. We're not sure where that line intersects that creek. How do we do that? Well, again, with mathematical tools, you can often calculate that if you can survey the bank of the creek and you can survey these 2 points. But one of the physical ways to do that is to actually set up your instrument here, backsight this point, invert your telescope, and you might set a point here, because that's on line because the ground is going up and down. Then you would move your instrument here, backsight this point, invert your telescope, and now maybe you're looking at the bank of the creek and you could set a stake where this line intersects. The danger in doing this is that you might have errors in your telescope. Same reason that you do phase 1 and phase 2 measurements, you should also do that here. So if we inverted the telescope here from, so backsighting here, we would have originally been in phase 1. So when we foresight here, we're in phase 2. Now what you do is you loosen the clamp, you come back here, and you backsight the same point in phase 2, and now in phase 1. It's very common when you try to mark that same point, you will see that it misses a little bit. Now how much will it miss by? Well, it might miss it by the width of a pencil line, or it might miss it by more than the width of a stake. It all depends. And so what you do is you take halfway in between the two for the true point on the line. And you keep doing that as you prolong it. And finally, I want to talk about 3 cases for establishing an instrument station on a line. So when you have 2 points, that exist, and you want to somehow set up on this line in some other location. How do you do that? Well, the most common way to do that is set up your instrument over one of the points, you sight the other point, so you have a line of sight that goes through this way, you mark a point, then you invert your telescope and repeat the same process, because the point you mark now may be slightly different for the same reason we talked about in the previous slide on prolonging a straight line. And now you have established a station so that you can set up your instrument there, and you know it's on the line connecting these 2 points. It's when the 2 points are intervisible, meaning you can see the other point from the first one. That's case 1. In case 2, the points cannot be seen from the other point. They're not intervisible, so looking at this in plan view, looking at it from the side, we have this situation. The land looks like this. We have a point over here, we have a point over here, and we need to set a point somewhere here on this hill. So if you look at this in, that's in profile view. So in plan view, here are the 2 points, and we somehow need to locate a point here. How do we do that? Well, it's not the easiest in the world, and what you do is you estimate your position, and you sight this point, and then you invert the telescope, and you may find that you missed this point by 6 feet. And you say, aha, so I need to move my instrument station a little bit this way, and if it happens to be near the middle, then it would mean you need to move about 3 feet. If you happen to be closer to one station or the other, then you either increase or decrease the amount of lateral offset. And then you keep repeating this until you get so close that the final movement can be accomplished by simply loosening the tripod fixing screw and moving the instrument on the head of the tripod without actually moving the tripod itself. So that's case 2. And finally, case 3 is where there's no visibility even in between. And so the most common situation for this would be where you have this kind of thing, and you have a point over here, you have a point over here. Again, this is the profile view. So in plan view, you pretty much have nothing. And so this is where you actually would run the equivalent of what's called a random traverse, connecting these 2 points. You'd figure out where this line is, and if you needed to locate a point, let's say here at the bottom of the creek, you would come over there and say, aha, I know that's close to this traverse station. And what you do is you can calculate the coordinates, the northing and the easting of where the point is that's on those 2 lines that's at the bottom of the creek. So this is generally the way these things are done. This takes mathematics that we won't get into here, but we will in surveying 2. The other 2 methodologies are certainly within your grasp. And with that, we will conclude this lecture.